Hi everyone, I'm Lynn, and today I'll be giving an update for my deep learning task focused on predicting early hospital readmissions for diabetic patients. That is, for someone who has been diagnosed with diabetes and discharged from a US hospital, the task is to predict whether they'll be readmitted to hospital within 30 days. This is important to improve patient outcomes and ensure better medical resource allocations. This is a binary classification task, and important to perform metrics are recall, precision, F1 score, and the AUC/RUC score. The dataset is sourced from the UCI machine learning repository with 10 years of real clinical data from 130 US hospitals, consisting of 50 columns and around 100,000 entries. And for pre-processing, I removed invalid rows, merged similar medical categories, dropped the weight and payer code columns, and only kept the first encounter for each patient. Overall, this reduced the dataset to around 70,000 entries. The EDA also showed that the dataset is imbalanced, with only 9% of patients being readmitted as shown by the distribution on the left. Hence, synthetic minority oversampling technique was later applied to generate synthetic samples for the minority yes class. For the first deep learning architecture, feed-forward neural network was chosen. It is a basic neural network where information travels sequentially in one direction through the nodes in the hidden layers and to the nodes in the output layer. During this process, weights and biases are updated based on the error calculated using backpropagation. Additionally, activation functions are applied within each node in the hidden and output layers to capture nonlinear relationships. This feed-forward model was chosen because it is a good starting point for tabular data and great for when there is a large dataset and nonlinear relationships present. Specifically, 3 hidden layers were used and activated using the ReLU function with a dropout rate of 0.5, and the sigmoid activation function was used as this is a binary classification task. The second deep learning model is the wide and deep neural network. It combines a wide model for memorization and a deep network for generalization. As seen on the left, the deep component is a feed-forward neural network that captures complex patterns, whereas the Y component is simply a skip connection that carries forward the input data. The two components are then concatenated and fed through as input for the output layer, of which an activation function is applied. This model was chosen as it can learn both simple and complex patterns in the data, which may lead to more accurate predictions. The model setup for the deep model is very similar to the first model, and the white component is simply a copy of the input layer. And the combined model uses sigmoid activation function again for the output layer. Besides the two deep learning models, a baseline model in the form of logistic regression model was fitted to the dataset. The results from all three models are captured in the table below, which each cell's color reflects the relative performance to the other models for that criteria. Note that the values are represented for precision, recall, and F1 score are macro averages of both the positive and negative classes metrics. It does not take the class imbalance into account, and this was chosen to reduce the effects of the imbalance, where higher importance is not given to the not re-emitted class, which has significantly more entries. All three models perform quite poorly and as seen in the consistently low values for precision, recall, F1 score, and the ROC-AUC score. The ROC-AUC scores around 0.5 suggest that the models are slightly better than random guessing. This poor performance is likely due to the complex nature of the task and the fact that it's an imbalanced dataset. Although the smart oversampling technique was applied, it might not have been effective in solving the dataset imbalance problem. These metrics were chosen because accuracy, as we can see here, is not a sufficient metric to evaluate the model's performance because of the imbalanced dataset and the medical context. For example, special emphasis should be placed on reducing the false negative prediction rate due to the medical context. Secondly, for both deep learning models, overfitting might be present due to significantly better metrics for the training set. And lastly, the wide and deep model performed the best overall due to its moderately better recall, F1 score, RAC, AEC scores, and the overall accuracy. Given this, the next steps are to perform hyperparameter tuning for the deep learning models and also incorporate entity embedding for the white and deep model. This concludes the presentation. Thank you for listening.